Hi, my name's James, and I'm the instructor for the AP Statistics course at Royal-Ivy. In this video, I'll walk you through the solutions to a few relatively challenging problems that may appear in the AP Statistics exam. Let's read through the first problem. A math competition uses the following scoring procedure to discourage students from guessing on the multiple choice questions. For each correct response, the score is 7. For each question left unanswered, the score is 2. For each incorrect response, the score is 0. If there are 5 choices for each question, what is the minimum number of choices that the student must eliminate before it is advantageous to guess among the rest? Okay, so first let's get organized. The correct answer, we get 7 points. Unanswered, we get 2 points. And then for incorrect, we get 0. Okay, so there are 5 answer choices, so let's kind of go through the thought process real quick. So A, B, C, D, E. Okay, so we have 5 answer choices, and given that we can't eliminate any of these choices, the probability of getting the correct answer when we randomly guess is 20%, right? It's 1 out of 5. Okay, and then if we eliminate one of the 5 answers, say choice E is definitely wrong, then our chances increase to 25%, right? So, and then if we eliminate one more, we get a 1/3, right? So our chances of guessing the correct answer increases, right? So let's say if we did not eliminate any of the answers, right, then it's not sensible, actually, it's insensible to just randomly guess, right? Because our chances of getting the correct answer from randomly guessing is 20%, and so in any circumstance, we're not going to guess when we can't eliminate any of the choices, right? And so given this condition, how many answer choices should we eliminate so that when we randomly guess, it's always better off, it's always expected to get us a higher score than if we were to leave it unanswered? So as we eliminate the incorrect answers, our risk goes down, right? So there's this certain point where guessing becomes a lot more strategic than leaving it unanswered. So that's the question. And so basically this covers the concept of expected value, right? So specifically we're supposed to find the expected value of guessing, right? And the expected value of guessing should be greater than 2, right? Because we would want to get more we would want to get a higher score by guessing rather than just leaving it blank. So, okay, so first let's get rid of this unanswered option because we're always we're just gonna guess, and so we're left with 2 outcomes here. Okay, and then let's create a table. For expected values, it's always good to create tables. And so we have correct and incorrect. Okay, and so when we get the correct answer, 7 points, incorrect, we get 0. And probability, let's say that we're not going to put 1/5 here, we're just going to say that we have n number of answer choices. Okay, because remember, we're trying to solve for the number of answer choices given a certain condition. And the condition being guessing gives us a greater expected value. So the probability of choosing the correct answer out of n is 1/n, and all the rest of the choices are the incorrect answers, so we'll say it's 1 minus 1/n. Okay, and so the formula for the expected value we know is the sum of the event times the probability of that event. Okay, and then we want this to be greater than 2, right? So equals 7 times 1 over n plus 0 times 1 minus 1 over n, and this has to be greater than 2. Okay, so when we solve for n, what we get is n is less than 3.5, and these are discrete variables, so we should be left with n equals 3 choices in order for our guessing to be more advantageous than leaving the question unanswered. But it asks for the minimum number of choices that the student must eliminate, right? And so not how many questions we are left with, we have to find the number of choices that we have to eliminate. And so that would be 5 minus 3 equals 2. Okay, that's the correct answer. Okay, on to the next problem. A large number of randomized experiments were conducted to determine whether taking a particular drug regularly would decrease the chance of getting a certain disease. For each of the experiments, the drug effect is the difference between the proportion of people taking the drug who got the disease and the proportion of people taking a placebo who got the disease. If the drug had no effect whatsoever, which of the following experimental results would be anticipated? Okay, statement number 1. P-values will be greater than 0.05 for about 95% of the experiments. Statement number 2. There will be about an equal number of experiments showing positive and negative values of drug effect. Statement number 3. When 95% confidence intervals for the population drug effect are constructed, those confidence intervals include 0 about 95% of the time. Okay. So let's break this problem down into... Okay, so a lot of students find these types of problems challenging. We just have to break down each statement, look at it one by one, and you'll realize that this problem is actually not so bad. Okay, so first, let's get organized again. I'll write down the null hypothesis and the alternate hypothesis, okay? Because I see p-value, that's what it's talking about. So null hypothesis, the drug had no effect, okay? And the alternate hypothesis is not H0, meaning there must have been some kind of difference between the two groups. And then I'll continue, and then I'll go ahead and write the conditions, right? So we know that in order to reject the null hypothesis, the p-value has to be less than 0.05, right? So to p-value has to be less than 0.05. And then the problem also just tells us that the drug had no effect whatsoever. So it tells us that the null hypothesis is true. So if the null hypothesis is true, then we fail to reject H0. And so p-value is actually not less than 0.05, it's greater than, right? P-values will be greater than 0.05 for about 95% of the experiments. So statement number 1 is true. Okay, and just to elaborate a little bit further, p-values represent the likelihood of the differences being by random chance, right? So if we have a high p-value, okay, if we have a large p-value, then that means it's quite likely that whatever difference that we saw between the two groups, whatever slight effect that we saw from the drug, it just happened by coincidence, okay? It doesn't actually have statistical significance, okay? So p-value large means likely observed difference is likely by coincidence, okay? All right, there will be about an equal number of experiments showing positive and negative values of drug effect. Okay, so this is also quite straightforward. If the drug had no effect whatsoever, then the differences we see in various experiments, right? It said a large number of randomized experiments, right? So across all these many randomized experiments, we should see an equal number of differences. What I mean by that is if the drug has no real effect, the differences we see in all these various experiments should be completely random. So sometimes the drug group might do slightly better by chance, and sometimes the placebo group might do slightly better. But over a large number of experiments, these differences should roughly balance out, with about as many experiments showing a positive effect as those showing a negative effect. Okay? And so statement number 2 is also true. All right, last one. When 95% confidence intervals for the population drug effect are constructed, those confidence intervals include 0 about 95% of the time. Now, let me write one more fact we can get from this problem, which is the drug had no effect, and so I'm going to say drug effect equals 0. Okay, so if this is true, if the null hypothesis is true, right, then this statement is saying that if the drug has no effect, the true effect is 0, and when we construct these confidence intervals from our experiments, if the drug indeed does nothing, we would expect the interval to include 0, right? The drug effect is 0, so it should include 0 about 95% of the time. So statement number 3 is also true, and so the correct answer is E. Okay, next question. A manufacturer claims its brand A battery lasts longer than its competitor's brand B battery. 9 batteries of each brand are tested independently, and the hours of battery life are shown in the table below. Provided that the assumptions for inference are met, which test should be conducted to determine if brand A batteries do in fact last longer than brand B batteries? So in the AP Stats exam, students are required to not only know how to conduct different tests, but also to understand when to use each type of test. And this is a good problem to get some practice. So let's first write down the different tests that we know. Okay, so first and foremost, we have one-tailed test, which is either A is greater than B or B is greater than A. Maybe that's a little confusing. I'm going to say A is less than B, okay? It's either one or the other, okay? And then we have the two-tailed test. And that's just test for whether there is any difference in A versus B. Then we also have the z-test. This is for large sample sizes. Where n is greater than 30. And this is because it assumes the sampling distribution of the mean is normally distributed by the central limit theorem. So assumes according to the central limit theorem. Right. And also population standard deviation must be known. And then we have the t-test. This is good for small sample size. And when the population standard deviation is unknown. Okay. And then we also have the paired t-test. Okay, so this is when we use this when the data pairs are dependent. On each other. Okay, so all right, now that we have written down some of the tests, let's look at the problem. So first, it says that the battery, 9 batteries of each brand are tested independently, so they are independent, and the sample size is n equals 9. Okay. All right. So firstly, since they are independent, we're gonna get rid of the paired t-test, right? Because the two samples are independent. And so we also have n equals 9. It's a small sample size. And we also don't know the population standard deviation. We have to estimate from the sample here, right? So SD standard deviation must be estimated. Okay, so I'm going to put population here. Population standard deviation must be estimated with a small sample size. And so it's quite unrealistic to use the z-test here. And then we have, so the manufacturer claims that the brand A battery lasts longer than its competitor's brand B battery. And so it's not whether there is a difference, right? So it's not a two-tail test, it's a one-tail test, right? And in this case, we're gonna opt for this one, right? A is greater than B. And finally, so we do have a small sample size of n equals 9. We do not know the population standard deviation, and so we should use the t-test. And so the answer to this question is going to be one-tailed t-test. Okay, this problem is about calculating probabilities. A complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any one year are 0.01, 0.03, and 0.04 respectively. If any one component fails, the whole device will fail. If the components fail independently of one another, what is the probability that the device will not fail in 1 year? Okay, so let's first start by writing down the probabilities of each component failing. So if any one of these happens, right? If any one of the components fail, then the entire device will fail. So the probability of the device failing is the union of each of these. Okay, and that is probability of fail. For this one, I'm talking about the whole device. So that means the probability that it will not fail is just 1 minus the probability A union probability of B union probability of C. Okay. And so how do we calculate this part here? So in the AP Stats exam, they give you a formula for calculating the union. Okay. In this case, it's going to be so this symbol here is the intersection. It means probability of A intersection B intersection C. That corresponds to the probability that A, B, and C all happens at the same time, all happening together. Okay, so and then now we have to calculate this intersection part. Okay, and we learned that if A and B are independent events, then the intersection between the probability of A intersection B is the probability of A times the probability of B, given that A and B are two independent events. And so we know that A, B, and C are all they all fail independently. They are independent events, and the problem tells us this: if the components fail independently of one another. Okay, so now we can calculate probability of A so B so C equals probability of A times the probability of B times the probability of C, right? And so now we can rearrange, we can rewrite the formula so that probability of the device failing okay, and now we can just plug in the values. So it's 0.01. And this comes out to about 0.079988. Okay, so this is the probability of failure, but we're looking for the probability that the device will not fail in 1 year. Means we're looking for this one. Okay, so P that is about 0.922. Okay, so the probability of the device not failing in 1 year is 0.922. So we've looked at just a few skill sets that students are required to know in order to do well in the AP Stats exam. If you need help in understanding the concepts a little deeper and really want to ace the subject, or if you have any questions, please contact Royal Ivy. Thank you for watching.